one announcement is I'm going to release homework number 5 on Wednesday. The homework will cover basically everything we have talked about transaction. And that homework will be due a week from Wednesday, meaning the next Wednesday. Which, after that, you're only left with phase 3 to complete. And I'm hoping I can wrap up the discussion on transaction using today's lecture and part of Wednesday lecture. Then moving on from Wednesday, I will talk about a little bit about the storage engine of database system, and also talk about NoSQL systems. Those, I will try to cover some of those through a quiz. I will let you know, what specifically will be covering the final test. Okay, so that's kind of roadmap for what's meant for this course. That being said, just a quick reminder: if you haven't started working on your phase 3, you should start right away. Don't wait a minute. No extension whatsoever. Okay. So if you haven't started working on it, you should get started. Speaking of which, any question on phase 3? So far, so good. Everything is good. If you follow the instruction I sent out, either you do it on the server or you do it locally. But that being said, I'm going to continue with the discussion on transaction. So last week we talked about isolation level. We talked about the ACID property of transactions. And among these 4 properties, we've been focusing on isolation. And in particular, we talked about 2 isolation levels. We talk about serializable isolation level and repeatable rate isolation level. Serializable isolation level basically says you can interleave action from different transactions as much as you want, as long as the end effect of your schedule is equivalent to a serial execution of those transactions. For example, if you have only 2 transactions, your schedule must be equivalent to either T1 then T2 or T2 then T1. When I say T1 then T2 or T2 then T1, I mean there's no interleaving of action of those 2 transactions at all. When you do interleave action from different transactions, your schedule must be equivalent to one of the 2 serial executions. In that case, it is called the serializable isolation level. If you satisfy that requirement, you are in the serializable isolation level. Okay? What about repeatable rate? Repeatable rate basically is what I said here. A transaction may not perform dirty rates. Dirty rates meaning that one transaction is reading a dirty item. A dirty item is defined as an item being written over by an uncommitted transaction. If you try to read an item that's been overwritten by another transaction who has not committed yet at the time of you reading the item, that's considered a dirty rate. Repeatable rate basically says no dirty rate, and an item read multiple times cannot change values. The key takeaway from this definition is it has to be an item read multiple times. Okay, it satisfies the repeatable rate requirement, isolation level. So that's just a recap of what we said, and we use this particular example to demonstrate the difference between serializable and repeatable rate isolation level to show you that repeatable rate isolation level really is just a relaxation of serializable isolation level. What that means is serializable isolation level will give you stronger consistency guarantees. However, that means that less throughput from your system because you're going to disallow more schedules if you go with serializable isolation level. The interleaving of action from different transactions will be more restrictive if you go with serializable isolation level. Taking this as an example, this particular schedule is not allowed under serializable isolation level for the reason I explained from last lecture, which I'm not going to repeat myself. If you don't understand why, go back and review that YouTube lecture from last lecture. Okay? But it is allowed under repeatable rate isolation level. Okay? Because there are no dirty rate, item like other time do not change values. Again, we have detailed the reason why this is allowed in repeatable rate, but not allowed in serializable isolation levels. In addition to these two isolation levels, there is also some other isolation levels that's well known in the literature. I'm going to write them down, but I'm not going to define what they are. Just FYI. There is the snapshot isolation level. There's the rate committed and rate uncommitted. Okay, this has this, a stronger consistency guarantee than this one. Rate uncommitted isolation level basically is like do whatever you want. Essentially, you can interleave action from different transactions as any order you wish. Henceforth, there is no guarantee whatsoever from the database engine. Meaning that in order to cope with a database engine like that, the application developer really need to understand what's going on. Okay? And enforce those consistency requirements from your application level code. Okay. Next, I'm gonna say a few words on these read-only transactions. The problem, the challenge, introduced by different isolation levels, is really caused by write operations. Imagine if you have a system with read-only transactions. Imagine you go to Amazon.com and every user of Amazon.com only do search, but never do any order or update. Okay? Imagine that's the case. Then you don't have to worry about this different isolation level at all. Why? Because there's going to be no conflict whatsoever. A rate will never conflict with another rate by another transaction, because you're not changing the values of what you're reading. So read-only transactions are friends of the database engine. The more read-only transaction you have, the easier to deal with for the database transaction engine. Okay? However, unfortunately, you have update operation. Like this is an example where we have read-only transaction, right? Let's imagine these two statements are from two different transactions. You can execute them in any order, interleave action from them in any sequence without worrying about what kind of consistency issues it may introduce. Does that make sense? Okay? So this standard default, don't take this for granted, by the way. It really depends on the application you are talking about. For a lot of banking operation, core banking operation, or imagine those transactions going to Wall Street as we speak. Those, you want to make sure you have strongest consistency guarantees. Because money is involved. Not only money, but a lot of money is involved. So you want to make sure those are done properly. So typically, they use serializable isolation level for those applications. Okay? However, serializable basically means you're going to limit the throughput of your system, because you're going to allow less degree of interleaving action from different transactions, which basically means less parallelism in your system, which lower the throughput of your system. Throughput is defined as number of transactions you can handle per second or per minute, some time unit. Okay? So, for example, typically people measure throughput using something called TPS. or TPM. Transaction per second or transaction per minute. This is similar to, all of you know how to drive a car, right? You have a dashboard. One of the important information from your dashboard is what?
RPM.
Yeah, RPM. You know what that is? Google it. You should know it if you're a driver. Okay. That's an important indication of how good your engine is. Okay? Your car engine is. Similarly, we don't have RPM, we have TPM or TPS. Okay? So weaker isolation levels basically means increased concurrency plus decreased overhead, which leads to better performance. But it does bring a weaker consistency guarantees. Some systems have default as repeatable rate. For example, the MySQL database server that we are using, the default is, as I demonstrated to you last lecture, is repeatable rate. It's using repeatable rate. PostgreSQL use snapshot isolation as the default. In fact, in most cases, in most practical applications, people actually use snapshot isolation. Okay. Next, I'm going to move on to other properties of transaction. Now we understand what I stands for, which is isolation. What about the other property of transactions? As we argued, the motivation for transaction is to not only to deal with concurrent access, but the other really important objective of using transaction is to be resilient against system failures. Resilient against system failures. Okay? So we need to define what do we mean by being resistant to system failures. So let's go back to the definition of transaction. Transaction is a sequence of one or more SQL operators treated as a single unit, as not just as a unit, but as a said this multiple times, as an atomic unit. Atomic unit basically means that you want to guarantee this all or nothing semantics. Right? All or nothing semantics. All or nothing semantics. So what do I mean by that? So a transaction is a sequence of SQL statements. And each SQL statement may potentially change the state of your database in a certain way. It may or may not. If it's a read-only statement, it does not change the state of your database. But if it's an update, insertion, or deletion statement, it will change the state of your database. You follow that? And you have a sequence of these statements who can potentially alter the state of your database system. So you start with a copy of your database, and then a transaction comes in. The first statement of the transaction changed the state of the database in a certain way. The next statement changed the database state yet to another version until this goes on until the transaction commits. Okay? If there's no system failure. What happens if system fails in between? Meaning between transaction has started and before transaction has committed. You want to guarantee this all or nothing, meaning that all the changes made so far by the current transaction, let's say I have executed, let's say this transaction has 10 statements, and I have executed half of it, 5 statements. And all 5 statements are update statements. Update database in different ways, and system has failed at that point. What you want to guarantee is all these 5 changes gonna be rollback. It's like none of the 5 statements had been executed at all. You cannot leave database in a state with, okay, you have 10 statements, halfway through system failed, you cannot leave the database in a state as if, okay, 5 statements have been executed, or 3 statements have been executed, or 2 or 1. It has to be all of them, either all of them, which is, you have committed, transaction has committed before system has failed, or none of these statements has been executed. This is the all or nothing requirement. This all or nothing requirement brings up the other 2 properties in transaction. One is atomicity. Atomicity really is to capture this atomic unit concept, right? Meaning that if system fails in the middle of transaction execution, meaning transaction has not committed yet, then you, meaning the database engine, has the responsibility to roll back the database to a state before that transaction has started. Before that transaction has started. This is non-trivial if you think about it. This is non-trivial. Why this is non-trivial? The naive solution, okay, to guarantee this is to say, okay, I'm gonna quote-unquote buffer the changes made by a transaction somewhere, but I do not reflect any of these changes to my database until that transaction has committed. When transaction commits, I'm gonna write all these changes all at once. This is an easy solution to guarantee atomicity. Because why this is the easy solution? Because if you do this, your database state is intact until transaction has committed, right? However, if system does not fail, you end up with a really heavy commit operation to perform. Let's say this transaction makes hundreds or thousands of updates. You buffer all of them somewhere without reflecting them in the database at all. And when system is ready to commit, you're gonna take all of this and apply to the database. This will take time. This will introduce a lot of overhead at the time of transaction commit. And this brings a lot of challenges, especially what if system fails during committing? Meaning commit is not an atomic operation if you do this. Does that make sense? And so this is not really a practical solution if you have a lot of transactions in your system. In practice, people do something different to make sure atomicity is guaranteed with efficiency and scalability. That's beyond the scope of this course. I'm not going to talk about how transaction engine actually is implemented to guarantee atomicity. But I do want you to realize the challenges associated with ensuring atomicity. That brings up my next discussion, which is what D stands for. D stands for durability. Durability can sometimes be understood as persistence, being persistent as well. What it says is very simple. Basically, it's actually referred to this all or nothing semantics, in particular this all part. What it says is when transaction has committed, given a transaction, let's say that transaction has committed. Once a transaction has committed, you, the database engine, has the responsibility to ensure that all changes are going to be permanently reflected by your database. And if you follow the discussion I said earlier, a simple solution is, again, to write all the changes made by that transaction at the time of commit. Meaning you do not allow a transaction to complete the commit process until all changes made by that transaction have been reflected in the database engine. If you do that, yes, you can guarantee durability. However, this again will make that commit process really, really heavy, really, really expensive, especially if you have a transaction who has made a lot of updates. Right? Imagine you buffer the changes made by this transaction. Initially, it's going to be nothing. Over time, it builds up quite a bit. At the time of committing, you have to write all this stuff to persistent storage. Your hard drive, your SSD. You cannot leave this in memory because memory is volatile. If you lose power, everything in memory is gone. That make sense? But imagine if this buffer size becomes so big, and you try to write this at once during commit, that will make the commit process super expensive and time consuming. What if system fails in the middle of your commit process? Right? This brings a lot of challenges. Henceforth, that's not the way people deal with, let me finish and I'll take your question. Henceforth, that's not the way to deal with durability. And people use something else to ensure durability, which I'm going to give you a quick overview of that, but I'm not going to go into the details of how that's done. Now I take your question. Go ahead.
Do database engines ever store multiple versions of the table?
Multiple versions of the table. That's a really good question, actually. This question concerns. To answer this, you need to understand how an update is performed in a database engine. Okay, by the way, I consider delete, insertion, and update all as update operation. Why is that? Because an update can be modeled as a deletion followed by an insertion. So all of these are actually the same type of operation. So to answer that question, you have to understand how updates are performed in a database engine. There are really two approaches to this, to address this. One is you do so-called in-place update. So each record is stored somewhere, as you can imagine, on disk. Okay? And when you try to update that record, you overwrite the original value of that record. Okay? So that's called in-place update. Another approach is to say, okay, I want to keep the original version of that record as it is. Then I'm going to remember a delta value somehow. This delta value will help me figure out what are the new value of that record. Let me give you an example. Let's say I have a student record. Student ID, name, age, GPA, login. And I'm only updating the GPA value of that student record. In-place update will take, original value 3.0 now becomes 3.5. Let's say this student did really well in this current semester, bump up the GPA value by quite a bit. Everything else stays the same. So that's called in-place update. The delta value, if you don't do in-place update, is to keep the original student record as it is. Somewhere else, I'm going to remember, okay, this student ID, this student record, the GPA value will become plus 0.05. That make sense? So which approach is better? Well, it depends. It really depends, right? If you do the second approach, and if you end up with a lot of updates to the same record, you end up with a lot of these delta values. And it's become super expensive for you to reconstruct the latest version of that record. Because what you have to do is take the original version and apply each delta in sequence until the end of that sequence to get the latest version of that record. Do you follow me? That's going to be super expensive. But the benefit it brings is that it allows the database system to reconstruct the version of that record anywhere in the history of your database. Meaning you can ask questions like, what's the value of the GPA field of this student 2 days ago, a year ago, 2 years ago? That makes sense? You just go back and trace back the sequence of delta values and figure out what's the valid version of that record given a query time range. You follow me? So those are the two different things. And if you do the second approach, meaning you are not using in-place update, you end up with what we call the multi-version database. And there are a lot of details going into that. I will stop right here in response to your question. If you want to understand more on that, you should take my grad level database class. For this class, we're going to assume we're using in-place update, meaning a single version database system. If you use a single version database system, if you think about atomicity and durability, this brings challenges, right? Because you don't want to, as I explained already, you don't want to buffer all the changes in main memory and write all of this to disk or permanent storage only at the commit time, as I have already explained. So what you want to do is you want to apply updates on the fly, even before transaction has committed, to give flexibility to the database engine to optimize how the engine going to manage this buffer. So the buffer can grow, can shrink. It's independent of when transaction going to commit. That will give the best performance to the database engine, as you can imagine. But this brings a lot of challenges, because if you allow an update to be applied to the permanent storage of you, so the power, say system failure. The system failure does happen. Does happen. Still flashing. Okay? Okay? So this is like okay? Perfect. Let's demonstrate to you system failure and how it's recovered. Okay? And where I was talking about, okay, I was talking about if you allow updates to be applied on the fly, independent of how transaction actually commits, this brings a lot of challenges for you to realize atomicity and durability. Why is that? If you allow an update to be applied before that transaction has committed, meaning the change will be reflected permanently on your disk. Now, what if that transaction later failed? Either the transaction itself decides to roll back, or it is forced to roll back because of the system failure. Now, you have to worry about atomicity, right? If that happens, you have to erase that permanent change caused by some of the statements from that transaction that you have applied to disk before that transaction has committed. You follow me? But if you do in-place update, how can you erase the change made by that transaction? Without any additional knowledge, this is impossible. If you have overwritten the GPA value from 3.0 to 3.5, how could you figure out the value was 3.0? Now to roll back the change. Without any additional facility, this is impossible. Right? So you do need some additional mechanism to facilitate you to do that, to ensure atomicity. Similarly, for durability, if you say, okay, again, go back to the motivation I said. You don't want to have a heavy, expensive commit process, meaning wait until all changes are made to this before you allow a transaction to commit. Meaning you allow a transaction to commit anytime, even if some of the changes are still in the buffer and have not been reflected on disk permanently yet. And you allow a transaction to commit. This will make the commit process a lightweight process. So transaction can commit anytime, and commit can be viewed pretty much like an atomic process. But if you do this, you still have some changes made by that transaction buffered in the memory and not reflected on disk. What if system now fails? Then everything in the buffer is gone. But that transaction has committed, and per the durability requirement, all the changes made by that transaction somehow need to be permanent. But it is not permanent in this case, because some of the changes are lost forever, and the transaction had committed. And how do you figure out those lost updates? caching the buffer when system fails for those committed transactions to ensure durability. Again, that's another challenge. You follow, the challenge associated with both of this? Yes?
Clarify. The ACID properties are guaranteed by the database engine?
Say again? Which property?
The ACID properties?
Yes, of course. Yes. Yes. Yes.
Are all commits sequential, or can they be in parallel?
Define what do you mean by sequential?
So as you're doing transactions, in the order they came in, do they get processed and made permanent?
Oh, you mean if you have multiple transactions, what's the commit order of those transactions? No, they can be random. Going back to the serializable acceleration level I said, the scheduling of those transactions, you can do whatever you want as long as it is equivalent to one of the sequential execution of those transactions. It could be T1 and T2 or T2 and T1. It doesn't really matter. Okay? And the effect of those might not be the same. T1 and T2 may not be equivalent to T2 and T1. But the point is, from the system point of view, from the database engine point of view, all I guarantee you is this serializable notion. If you really want to make sure T1 has to be executed before T2, then your application level code do not start T2 until T1 has committed. That's the application level guarantee that you have to enforce. If you say nothing from your application level code, then the database engine will do whatever the isolation level allows that database engine to do. You have a question over there? Go ahead.
It's not questions. Is the system just going to automatically roll back whatever you made during that transaction?
So we're actually going to talk about concurrency control a little bit. Among these 4 properties, I'm not going to talk about how database ensure A, C, and D, even though I had a little bit of discussion to demonstrate to you the challenges associated with this. But I do want to talk about isolation in further details. So your question will be answered in a minute. Okay, isolation is achieved by locking, which I'm going to skip this part because I have a dedicated slides for this coming after this. Durability and atomicity are guaranteed by logging. The basic idea is, instead of working with the actual updates, the actual updates are to be applied over records. And a buffer, that means a buffer, and the buffer behaves in a way that's independent from your transaction processing. Meaning that buffer can take an uncommitted write and write that permanently to disk. Buffer can also buffer a committed write in the buffer long after that transaction has committed, and without writing it back to disk. All of this creates a lot of challenges for ensuring atomicity and durability. And how do I ensure I can perform a rollback for uncommitted transactions if system has failed? To do that, I use something called logging. The basic idea is you write down what you're going to do, but you don't actually do it yet. You haven't actually done it yet. But you write down what you're going to do. For example, using that update student JPA value as an example, I'm going to write down somewhere to say I'm going to update student ID 101 JPA value from 3.0 to 3.5. If I have this documented, I can do the so-called undo operation. If a committed write is pushed back to disk already. Why? Because I can look up this journal entries and realize, oh, the old value was 3.0. So I can revert back to 3.0. I can also, later on, if some updates are buffered in the buffer and from a committed transaction but have not been written to disk yet, and system fails, if I have this journal entry somewhere, I can still reapply this update to set JPA value from 3.0 to 3.5. Suppose that's from a committed transaction. Okay? You may wonder, okay, to do this journal entry has to be permanently documented somehow. Otherwise, you run into the same challenge, right? And if you do that, it isn't the same as just applying the updates at the commit time. Well, the key observation is to document what you plan to do. is always way cheaper than actually performing the update operation. Why is that? Let's take the student record update operation as an example. To update the actual student record, you have to take the whole student record, which may have, I don't know, like 20, 30 additional attributes. You change the GPU value, then you write this additional whatever 20, 30 attributes together with GPU value back to disk. This is super expensive, as you can imagine. But update typically touch only a few bytes or a limited number of attributes of a given record. Rarely you're going to update the entire record. Henceforth, to document this journal entry with only affected part of your record from the update operation is way cheaper than remembering the actual update itself or performing the actual update itself. That's the catch. That's the catch. So kind of like, I'm gonna go to Toyota dealership to do an auto change using syncactic off. This is like a journal entry to document what you plan to do. This is way cheaper than actually go to the dealership, wait in the line, get your oil change done, and come back. You follow me? That's an example of it. So you are making the journal entry, which is we call logging, somehow persistent without performing the actual updates. Think about that oil change example I mentioned. Let's say a disaster strikes Salt Lake City, earthquake, whatever. If you remember you're going to do the oil change, after the earthquake is gone and Salt Lake rebounds, you can still go and do the oil change. Right? Like nothing had happened. Okay? That's kind of the way you understand this. Of course, there's a lot of details. It's not a trivial topic, by no means. But given the limited time I have for the undergraduate class, that's kind of as far as I can tell you about the challenges as well as how we actually address that. If you're super interested in those, take the grad level database class, and one day you become a database kernel developer. Like you work for Oracle, you work for Microsoft, you work for Google. All these companies like Google, Microsoft, Amazon do not sound like a database vendor to you, right? But if you go to their cloud service, everybody is building database, cloud database. Like machine learning is super hot nowadays, right? But if you think about all these machine learning applications, you got to run over some data stored somewhere. If you don't have your data properly stored, garbage in, garbage out. No matter how fantastic your machine learning algorithm is going to be, you're going to train a wrong model. That make sense? It's kind of like a kettle with boiling water. You train a model, you say, oh, that's hot. Then the association, if degree over 100 degrees, it's not going to be hot water, don't touch it. However, if you document this wrong, you say a kettle with boiling water is 20 degrees only, which is obviously wrong because your database did something really weird. Then you're going to train a model, oh, if the water temperature is 20 degrees Celsius, I'm talking about, don't touch it. That's the wrong model. Do you see the problem with it? This cloud vendors, why they're interested in building database, because that's how they attract users, companies, individuals, governments, to put their data on the cloud. If you don't have their data on the cloud to begin with, no matter how many fancy applications you build on top, nobody's going to use your cloud service. So you have to have a reliable, efficient, scalable database engine to begin with. Okay, that's why they're interested in this. But for most of you, I guess you probably don't worry about this because for most of you, you're going to be a database application developer, meaning you view database as a black box, to write application on top. But even if you just want to do that, you need to understand what is being guaranteed by this black box. You need to know that in order to operate this. It's kind of just like you don't have to know how to build a car, but you have to know what's coming out of the car in order to drive it. Like if you turn your wheel this way, you're going to turn left. Sometimes this is not that intuitive, right? If you fly an airplane, you push back, you're going to fly up. If you push down the steering wheel, right, of air flight. So it's not always that intuitive. So you need to understand what that black box guarantees for you in order to operate it, even if you don't want to know how that black box will be. Okay, so that's durability. Similarly, for atomicity is also guaranteed by logging. So we talk about rollback and all that, so I'm going to skip that. The last property we haven't talked about is consistency. C stands for this, the definition of this, to understand this, you have to understand what is functional dependency, which is what we have covered. Okay? So if you understand what is functional dependency, you should have no trouble in understanding consistency. C in transaction basically says the following. If every single transaction, note that a transaction is viewed as an atomic unit. If that atomic unit starts with a consistent database state, what do I mean by consistent database state? A database is in a consistent state if and only if all functional dependencies are satisfied. Okay? That's a simple definition. And if a transaction starts with a consistent state, then the requirement is that transaction must leave database in a consistent state. I don't care how you execute that transaction, you can do whatever you want, but at the end of the day, database must be still in a consistent state, meaning all functional dependencies are still satisfied. This is defined with respect to one single transaction, okay? You understand that? Now, what if you have multiple transactions? Well, simple. Before the start of any transactions, from this multiple transaction you're going to run, database start at a consistent state. Let's assume that. At the end of executing this multiple transaction, I don't care how you execute them, how you interleave them, you can do whatever you want. It's kind of like I leave 10 guys in a room, I say good luck, they fight, they do whatever, at the end of the day they all commit, they tell me come back. I come back and go in check, everything is still consistent, meaning all functions are still satisfied. That's all I care. That's from the eye of consistency. Of course, you have to worry about the other properties too. Do you follow me? So that's called the consistency requirement. Okay? That's called the consistency requirement. So this has to do with ensuring functional dependencies are guaranteed, at any state of your database while you're executing multiple transactions. So that's kind of the overview of transactions in database engine, right? The takeaway message is really just this: ACID. If you guys are a database developer, you need to at least understand this. When you are running a database application with multiple users, these multiple users may issue multiple transactions. In the very least, you need to understand what ACID stands for, okay? While writing your application. Now, as I said, I don't have time in this course to talk about A, C, and D in details, like how database engine ensure those. I'm gonna use I as an example because this is probably the most frequent property that application developers deal with when writing applications. So, which means you probably need a deeper understanding what this isolation is and how it is guaranteed by the underlying database. Okay. For that reason, I'm gonna dive into this isolation topic a little bit more. Okay. And that's what I'm gonna do next. Okay. So far so good. This brings up this topic called concurrency control, because isolation is all about concurrency control. While we're talking about I'm gonna assume that A, C, and D are guaranteed somehow. Somebody is taking care of A, C, and D for us. How? I don't care. Somebody is doing that. Okay? And to guarantee those, I assume they don't interfere with how I guarantee I, isolation. Okay? That's the assumption of our discussion here. Okay? In practice, ensuring isolation with concurrency control has implications to how you guarantee A and B in practice, okay? Which I'm gonna ignore for the discussion here, okay? Which I'm gonna ignore for the discussion here. Okay, concurrency control is this semaphore thing, right? These are your transactions. Too bad you cannot afford to build a dedicated rail for each transaction in your system. You just cannot afford to do that. So you put, you build a few rails, but you are running way more number of trains than the number of rails you have, and you want to make sure they don't kind of run into each other, right? That's kind of a high-level, metaphor I'm going to use for the discussion to follow, right? That's kind of what you're doing. I mean, of course, this is important. If you don't do this right, things gonna happen, right? Disaster gonna strike. Train gonna collide, and people gonna die, and stuff, right? But seriously, if you run a database without proper concurrency control, people are gonna die. No kidding, right? Because whatever system you are using, most system you are using nowadays, behind it is a database system. And if that database system ends up storing wrong values, because you're not running a proper concurrency control protocol, disaster is going to strike. Okay? So let's see how we get this right. So this is just a review of transaction. I'm going to skip that. And concurrency, again, I talked about this already. This is just a review. Okay? So I'm going to skip all of this. Now I'm going to use this simple example, really simple example, to demonstrate to you two things. One is the subtlety of this challenge. Secondly, to convince you that if you don't do this right, a lot of things in our society simply stop functioning. You cannot have a functioning society if you don't do concurrency control right in your database. That sounds like a really bold claim, but I'm going to convince you of that, using this very simple example, really extremely simple example. Okay? So follow with me. This actually is a really interesting, even though it's a really simple example, but it's actually a really interesting example. Okay? Okay, let's see what happens in this example. Okay, let's assume I'm talking about a banking application, a banking database, like Wells Fargo or Chase Bank, whatever, right? You guys all have a bank account. Now, what I'm doing here is A and B are two bank accounts. Okay? Assuming I own these two bank accounts. I have two accounts, a checking and a saving account with Wells Fargo or Bank of America, whatever. And all I'm doing, I'm transaction one, is to issue a balance transfer between the two accounts. $100 transfer between those two accounts. Let's say, today is my lucky day. The bank decides to give 6% interest to all my accounts. That almost never gonna happen, right? But imagine they're so nice, they're gonna give me 6% interest to all my accounts. Okay? And that happened to run roughly around the same time I'm doing my balance transfer. You see that? Very simple scenario. You may wonder what can go wrong. So what's the big deal? You transfer $100, you get 6% interest. What's the big deal? How can this possibly go wrong? Okay? If you really have true isolation, meaning that every transaction run by itself, and another transaction wait until one transaction has committed, yes, you're going to have no problem. Meaning if you do T1, then T2, or T2, then T1, in this particular case, the effect of this are the same. The effect of this are the same. You move $100 over to, let's say I have bank account A, the value initially equal to X, bank account B initially equal to Y. At the end of the day, no matter which sequence you are doing, the effect is very simple. The effect gonna be and bank account B will end up with, you can check this yourself, but at the end of the day, that's what you end up with, which is fine. You follow me? If you do this or this, you always end up with this, which is totally okay. Nothing goes wrong. What if you start interleaving actions from different transactions together? This is assuming you're doing true isolation, meaning one after another, which is okay from a semantic point of view, but from a performance point of view, it's really bad. What if I imagine, okay, I'm just making this argument up, right? Let's say I'm doing T1 and T2, and I physically withdraw $100 from an ATM, go for my lunch, and I even have the time to enjoy a coffee. And sometime in the afternoon, I'm like really bored, nothing to do. I go back and deposit $100 to bank account B, and then I declare my transaction is done. You're willing to give me 6% interest, sorry, you have to wait. If I do this. You follow me? If you're really gonna execute this in true isolation isolation fashion, you have no performance, you have no scalability, all of this are gone. Forget about it. But from a semantic point of view, this guarantees correctness, that nothing can go wrong. You follow me? Now you say you are like a bank database developer, you say this is bad. Fifth is holding us hostage. Let's do not wait for him come back and deposit $100. Let's go ahead with 6% interest increase. You follow that? So you're interleaving action from different transactions now. And you may wonder what can go wrong. Let's do that. Okay, let's do that. Okay, let's do that. What I'm going to do is, this will be time. So this is time. Let's say I'm going to interleave them somehow. The first way I'm going to interleave them is, okay, if and the bank said, oh, this is really bad. I'm going to get a database developer to do this. And they look around and say, oh, you're the best person. Fifi is the best person. You're teaching database, right? So why don't you do this for us? Interleave actions, improve performance, and I say, fantastic, I will do it. So if the bank asks me to do it, what I will do is the following. Okay, that's what I will do. How many of you think this is okay? If that's my account, I think it's okay. But if you're the bank, would you agree with this? Are you gonna go with this? If you say you're gonna go with this, do open a bank. I'm willing to invest on you, and I will store all my money in your bank. All right? And you go bankrupt in no time. Do you figure out what's wrong with this? No? Still no? Come on, you guys are computer science students, right? You have to figure out what's wrong with this. What's the value of A and B in the end of the day if you do this? What's the value of A? What's the value of B? Using this X, Y notation. Can someone tell me? What's the value of A in this case?
106.
Huh?
106?
No, it's not 106. It's x plus 100 times 1.06. X itself, the base, get that 6% interest as well. What's the value of b in this case?
1.06y.
Huh?
1.06y, and then minus 100.
Fantastic, very good. Value of a is okay, but value of b is not okay. The bank is losing $6 in this process. You may wonder, $6 is nothing, right? I mean, come on. Okay. Let's say I'm not Feifei anymore, I'm like Bill Gates. Trust me, Bill Gates will never transfer $100 because the time it takes for him to transfer $100, he probably make millions in the same amount of time because he doesn't bother to transfer $100. Trust me. So will he bother to transfer? Probably, I would guess. It's not even a million. A million to him is like $10, right? So let's say 100 million. 100 million, that's 10 to the power 8. Now, if you're the bank, you probably don't care, Feifei transfer $100, get $6 more, and you are losing $6. You probably don't care about that. But if I'm talking about 100 million, 6% of that, how much is that? Someone check this one. That's 6 million. 100 million, 6%, that's 6 million. And I guess if you're the bank owner, now you care. Still don't care? Still don't care? 6 million is, I care. Maybe one day I won't care, but for my current state, I still care. Okay? For me, I really don't care about $6. I grow out of that phase. Trust me. I don't even care $600. Okay? To me, that's like nothing. But 6 million, I still care. Seriously. Okay, you may wonder, do you see what's wrong with this? I hope all of you follow me. Now, you may wonder if that's the case, they're gonna favor us all the time, right? Let's, this is great. Let's build database this way. However, it can go both ways, as many things in life. I mean, as almost everything in life. There's no free lunch. Sometimes you win, sometimes you lose. It's a fair game. Now, if bank, again, tell me, okay, Feifei, this is not your account. This is like one of your students' account. Whatever benefit you can reap out of them from them by implementing database, you get 50%, bank gets 50%. Now I'm motivated to design a scheme that favors the bank, if that's the case. Do you follow me? So if that's the case, what am I gonna do? I'm gonna do the following. Okay? If bank tell me that's what I'm gonna do, I got 50% profit from whatever benefit I can bring to them, I will say, okay, let's not do this. Let's do the following. Okay? Now, what's wrong with this? Can someone tell me what's wrong with this? Are you gonna be okay with this if you are the owner of this account? If you say you're gonna be okay with this, fantastic. I'm gonna put all my money out and open a bank. Come, be my customer. Seriously, I mean it. It's easy money for me to make. So, which means you should not be okay with this, by the way, okay? Why you should not be okay with this? Can someone tell me what's wrong with this? Can someone tell me what's wrong with this? What's the value of A and B at the end of the day?
Is X times 106 plus 100.
What's the value of B?
B is Y minus 100 times 106.
Okay. Very good. So in this case, the value of B is okay, but not the value of A. meaning the bank being the winning side, and the bank account owner being the loser in this case, meaning the $100 somehow didn't get that 6% interest. You're losing $6. But you are losing $6. Now you may wonder, okay, again, I don't care, that's $6. But if I change this to 100 million, then you're losing. I mean, you're losing $6 million. You're losing $6 million. No matter how that can happen, well, you look at the stock market in the past few days, 6% is nothing. It's so volatile. My stock can't change more than 10% in the past few days, plus minus. So it happens. You follow me? And I'm sure you're not okay with losing $6 million. If you're okay, I haven't done my lunch yet. How about you treat me for lunch? That's like just $20. Okay? Seriously, I haven't done my lunch yet. If you're okay with this, let's go for lunch together. Not 6 million, it's just $60. Okay? I do easy lunch. I hope I convinced you, if you don't do this right, stuff gonna happen, right? And this is just a bank database, for God's sake, right? What if this is like FBI database, an NSA database, right? Or database for the military, database for Air Force Base. Stuff gonna happen, right? So if you don't do this right, imagine what's gonna happen, right? So how do we do this right? How do we do this right? Of course, you may wonder, by saying these two examples, you say, okay, that's too scary, right? Let's do not interleave actions. When we do that, stuff gonna happen. Let's go back to just this. As soon as you go back to that, Fifi gonna come in, withdraw $100, go for coffee and whatever, come back 6 hours. So nothing gonna perform. You follow the motivation here? So again, that's not okay. Okay. So how do we do this? That's what I'm gonna explain to you next. How do we do this right? Before I do that, I need to convince you that it is possible to do this right. If it's not, if there's no way of interleaving this and still things still gonna be right, we should just give up. We should adjourn the lecture, go for lunch. Right? Because no matter how hard you try, there's no way of doing this right. So I'm gonna convince you that it is possible to interleave actions and still do things right. In fact, it's fairly straightforward to do that. If I do this, what should I do? How do I change this to make things right? In this case, all I need to do is to do something like this. You follow me? You follow what I'm doing here? As soon as you make this change, everything suddenly becomes okay. Meaning that it's as if this. As if, because you are not actually doing this, but at the end of the day, it's as if you were doing that. Okay? So I hope I convinced you it is possible to do this right. In fact, this is not the only schedule to do this right. There are many other ways of doing this right. And still allow interleaving of actions. The next challenge boils down to the following, which is, now imagine if you're, if I can squeeze you to this little, put you into the database engine, we can adjourn the lecture. You can figure out how to do this right. But I cannot do that. So how do I figure out something that runs inside the database engine to do this right automatically? You follow me? That's kind of what we're going to discuss next. Okay? And this is, by the way, only 2 transactions. This is only 2 transactions. And imagine if you go to, so they don't show this. I want to show. Okay, I don't want to waste my lecture time. I'm gonna figure this out and show you next time. Basically, I want to show a stock, symbol, and show the real-time buy and sell transaction against that stock. Okay, there are millions of transactions being executed in real time. Okay, by different brokers, by people like you, all over the place. And how do you? And we're talking about just 2 transactions. That's like already hard. Like millions of transactions. How do you do this right? I mean, obviously it's not trivial. Right? Obviously not trivial. So how do we do this right? Okay, let's start with the abstraction of the problem. Go ahead.
I'm kind of confused by your example because shouldn't like the bank give the interest or value the interest at like a specific time? Like they don't. It's
not atomic. If you have millions of accounts, how can you make sure 6% interest are given to all accounts at the same time? If you can do that, I'm gonna open a company. Let's do that. If you have millions of accounts, you're giving 6% interest. How can you guarantee that happen at the exact same time? It takes time.
So they do it per transaction.
Of course, you ensure this in transactions. Everything, nothing in this world, physical world, is really atomic. You gotta really remember this. It takes time to do everything. Okay? It's not gonna be atomic. Nothing, no 2 things can guarantee to happen at the exact same time.
No, but you could give a timestamp and then say everything.
But I don't care how you do this, right? The timestamp, whatever you want to do. But the point is, what you said is not going to be doable in practice. Right? Okay. Now, let's think about how we abstract this problem. I actually don't care, from database point of view, I actually don't care whether you're transferring $100 or $100 million, or you are giving 6% interest, or 10% interest, or 1% interest, or 100% interest for that matter. From my point of view, all you are doing is a sequence of read and write. In particular, using this as an example, from my point of view, it asks you schedule. From my point of view, transaction 1, read the value of A, do something with it, and come back and write the value of A. So read A followed by write A. Similarly, for transaction 2, from the eye of the database engine, you are reading the value of A, you do something about it, you write the value of A. Again, you read the value of B, you do something about it, you come back and write the value of B. I actually don't care what are the difference between this B and this B. Whether it's 6% difference or 10% difference or whatever, I don't care. From my point of view, you ask me to give you the value of B, I give you, you do something with it, you come back with a new value of B, you ask me to write it back. Similarly here, you read the value of B, you do something, then you come back, ask me to write the value of B. So that's gonna be the abstraction we're gonna use. You actually don't care whether it's $100 transfer or 6% interest. It's the sequence of read and write. Do you follow that? Now, after we have done this abstraction, now we can start reasoning about how this is done. Your problem boils down to the following, which is given multiple transactions, where each transaction is simply a sequence of read and write on different objects in your database. Now, you throw away all those business logic. $100 transfer, 6% interest, update JDA from 3.0 to 3.5. You throw away all those business logic. Now you are simplified to a sequence of read and write of different objects. You follow that? Each transaction is nothing else but a sequence of read and write on different objects. Okay? And in particular, we're going to focus on, by the way, the focus of this class is, on serializable isolation level. Okay? Serializable isolation. We talk about different isolation levels, but for the purpose of this discussion, we're going to focus on serializable isolation. We're going to focus on this. We're going to focus on serializable isolation. In serializable isolation level, you allow only serializable schedules. Serializable schedules. What do I mean by serializable schedule? This, requires some, clarification. In order to understand serializable schedule, let's first understand serial schedule. Serial schedule is essentially a permutation of the input transactions. Without interleaving actions. Serial schedule is basically a permutation, a random permutation of your input transactions without interleaving actions. And we actually talked about this last lecture, and he, Wes, responded with, given n transactions, how many serial schedules you have? We discussed about that. You have n factorial serial schedules. Right? Why? You have n position to fill. The first position has n choice. You choose one of the transactions. Right? Execute all of that. Then the second position is left with n minus 1 choices. You go on, so it becomes n times n minus 1 times n minus 2 until 1. That's n factorial. So you have n factorial serial schedules when you do not interleave action from different transactions. All of you okay with this? So all of this is schedule. Why? Because you are executing transaction in sequential order. All of this, okay. Now, next we're going to talk about equivalent schedules. The equivalent schedule basically says, I take two schedules of the input transactions, and you can interleave actions from different transactions as much as you want, and in any order as you wish, in those two schedules. But at the end of the day, if the state of the database are equivalent, the states of the database are equivalent, after executing those transactions according to the two schedules, those two schedules are called equivalent schedules. Do you follow me? Right? So basically, you're checking the end state of your database. If the end state are the same, the two schedules are the same for the same set of transactions. You execute them differently, interleaving them as much as you want, as any order as you wish. At the end of the day, the state of the database, when two transactions commit, the state of the database are equivalent. That's called equivalent schedule. Okay? Now, with these two being said, it's really simple to define serializable schedule. You can actually guess what's a serializable schedule. A serializable schedule is a schedule that's equivalent to a serial schedule. That's it. That's a serializable schedule. Okay? For example, this, the top one, that's a serializable schedule. This one. This is a serializable schedule. Why? Because that's equivalent to T1, then T2, which is a serial schedule. This is a serial And that schedule on top is equivalent to this schedule. Henceforth is a serializable schedule. Do you follow me? With this definition, by default, a serial schedule is always a serializable schedule because a serial schedule is equivalent to itself. So henceforth must be a serializable schedule. That's the trivial kind of results you have. That's good. The one from here, this one, is not a serializable schedule. Why is that? Can someone explain to me why this is not a serializable schedule? Why this is not a serializable schedule? Go ahead.
Because of B. Because the value of B after.
Yes, you're giving some. I want to, from the definition of serializable schedule, can you explain why this is not a serializable?
Because it's not equivalent to.
Yes, because it's not equivalent to any of the serial schedule. It's not equivalent to this. It's not equivalent to T2 then T1. You only have two serial schedules in this case because you only have two transactions. Factorial 2 equal to 2. If you are not equivalent to any of your serial schedule, then you cannot be a serializable schedule. Okay? All right. Okay? So that finished the discussion on serializable schedule. Now, once you understand this, in serializable isolation level, all serializable isolation level says is that it only allows serializable schedule, period. That's it. That's serializable isolation level. I only allow serializable schedule. You follow me? Yeah? Now that means that the next thing is kind of tricky but important to understand as well. I'm going to draw a diagram for that. So this is, let's say, the set of all possible schedules for a given set of transactions. Okay, set of all possible schedules. And this somewhere is going to be the serial schedules. Okay? You follow me? Yes? So far so good? Serializable schedule is these guys. Such that any dot here is equivalent to some, not all, because not all serial schedules are going to be equivalent to each other. We argue that one. Serializable schedule says the effect of this must be same to one of the serial schedules. Okay, that's the kind of the relationship we have. The next thing I'm going to say is kind of tricky but important to understand. Now, the definition of serializable schedule allows you to check if a given schedule is serializable or not. This is kind of like, when we talk about functional dependency, we said, okay, if right, we have this theorem that if you decompose R into X and Y, if intersection of them determine X or Y, this is lossless. You can use this to check if a given decomposition is lossless, but you cannot use these results to actually perform a lossless decomposition. You follow that? In life, there are many such examples. Sometimes to verify something is easy, but to actually do it is hard. Right? To verify if that's a house, most of you, I hope all of you can do that. But to build a house itself, I cannot do it. You see what I'm saying? But this is an example where the verification of the problem is easy, but solving the problem itself is hard. But there are also some examples where the verification and solving are equivalent. For example, to verify 20 plus 20 equals 40. This is, verifying this is as hard as solving it. Because the only way to verify it is to do the bam calculation, 20 plus 20 equal to 40. You see that? But to verify at the house, you don't have to tear down that and build using all the equipment back to the house. Okay? So what I'm saying here is this gives you a way to verify if a decomposition is lossless, but it doesn't actually allow you to perform the decomposition. How do you perform the decomposition? Do you remember? The WZ thing, right? You decompose into, right? This is how you perform this. Similarly, what we said on this slide is to verify a given schedule is a serializable schedule or not. But we haven't talked about how you actually find those schedules. Meaning, how do you go from this huge space? This space is huge, by the way, if you allow interleaving of different actions. Even without interleaving, you already have n factorial. N factorial, by the way, is big. N factorial is roughly in the order of 2 to the power n. It's exponential. That's without interleaving. With interleaving, it's going to be super big number. So this is going to be a huge set. And how do you find those serializable out of this? How do you actually do the serializable schedules instead of just verifying it? We're going to talk about that on Wednesday, as we figured. Okay? Okay.
What was the stuff at all?
Oh, is that equal 4?
Yeah, it's not playing.
Is that equal 4?
Yeah.
Yeah, it's a 4.
Oh,
I saw it.
I didn't check this morning. I checked on Saturday.